Good morning, students. In this session, I will discuss some more problems related to Butterworth low-pass filter using bilinear transformation. So, IIR filter design. So, Butterworth low-pass filter and bilinear transformation techniques. So, how the because according to the different given specification, you should be able to realize the filter. Now, using bilinear transformation, we'll design low-pass filter having cutoff frequency. The given specification, you have to be very clear with the given specification. So, design a low-pass filter. So, cutoff frequency, the cutoff frequency desired, the cutoff frequency, the low-pass digital cutoff frequency we are going to design. So, having a cutoff frequency FCD is equal to 100 Hertz. So check the desired transfer function. Okay, desired transfer function h of z is stable or not. Find out the stability also. So assume that the sampling frequency is given here. The sampling frequency is equal to 625 hertz. 625 hertz. So the transfer function of the prototype. So you know that the normalized low pass unlock filter. So it is h of s. So normalized low pass filter, okay, which is equal to, so put s is equal to s by omega c. So in which there is a put s is equal to s by omega c. We'll take the second order transfer function. Take n is equal to 2. Okay, so in which the h of s will be, we'll get omega c squared by s squared plus 1.414 omega c into s plus omega c squared. So that way you know h of s is. So the unlock cutoff frequency, next one, unlock cutoff frequency, what's the form of the relationship between 2 by t tan omega t by 2. Here only, so you have to apply the given specification, 2 by t tan of, what is omega? 2 pi, you can write 2 pi f into t by 2, because the given specification f is given. So we can write 2 by t tan of 2 into pi into, what is f is given, 100 hertz into t by 2. So this 2 will be cancelled. So simplify. So t also given. What is it? T, the sampling frequency is given. So t is equal to 1 by fs. Okay. So what is the sampling frequency is given? 1 by sampling frequency is 625 hertz. Sampling frequency is 625. So you substitute this 1 by 625 hertz. So we'll get 1.6 milliseconds t. Okay. Now you can substitute 2 by 1.6 into 10 power minus 3 tan of 100 pi into 1.6 into 10 power minus 3. So use calculator, compute properly. So we'll get omega c is equal to 687.2 radians per second. So now you can write the h of s is equal to omega c square, 687.2 the whole square divided by s square plus 1.414 omega c into 687.2 into S plus omega c squared 687.2 the whole square. So next you find h of z. So h of z, use bilinear transformation, put s is equal to 2 by t z minus 1 by z plus 1. So h of z is equal to 2 by 2 by t. So what is the t? 1.6 milliseconds into 10 power minus 3 into z minus 1 by z plus 1. So which is equal to, you compute this value, so you get 1250 of z minus 1 by z plus 1. This is s. Put s is equal to 2 by t. So compute and substitute this value into h of z. So the numerator terms are 687.2 the whole square divided by s square. This is s. So 1250 s square into z minus 1 the whole square by z plus 1 the whole square. Okay, then plus 1.414 into omega c is 687.2 into s. So into s is 1250 z minus 1 by z plus 1 plus omega c square 687.2 the whole square. So compute h of z, use calculator step by step and find the value. So the numerator, I'll write the final values here. You just cross check z square plus 2z plus 1 divided by 6.89 z square minus 4.62 z plus 1.73 h of z. So you can take this denominator different ways. The denominator coefficients, denominator quadratic equation, the denominator, the quadratic equation. Solving this equation, so which is equal to minus b plus or minus root of b square minus 4ac by 2a. So you can write minus of minus 4.62 plus or minus root of b square. So ax square plus bx plus c. So ax square plus bx plus c minus b square minus 4.62 the whole square. Okay, minus 4 into a into c by 2a, 2 into a, 6.89. So simplify this quadratic equation and you will get 4.62 plus or minus j 5.132 divided by 13.78. So again you can simplify. This will be 0.336 plus or minus j 0.374. So since the poles are located, you can say that since the poles, how do you, okay, the poles z plane. So in the z plane unit circle, all the poles for stability, all the poles should lie. This is a unit circle. Unit circle 0.336. So this is j. Okay, j unit circle. Um, so in the z axis, so 0.336 plus j 3.74 plus or minus. So since the poles lie inside the unit circle in the z plane, the h of z is stable system. The question is whether the given system is stable or not. Okay, and you can write the denominator polynomial coefficients properly as per the given required transfer function. Then you can realize the system in that form too also. So how the questions and how the specifications are given, according to that you can conclude whether the given system is stable or not, and if you want to realize the system, you can realize the system. So one more problem we'll discuss. Convert. Next problem, another problem. Convert the analog, because this is John Procky's problem only. Convert the analog filter. The problem is convert the analog filter into digital IIR filter by means of bilinear transformation. Okay, so analog filter transfer function is given. So s plus 0.1 divided by s plus 0.1 the whole square plus 16. Okay, in the given specification, the resonant frequency omega is given pi by 2 and t is given 0.5. Okay, so the digital resonant frequency, is given. That is a digital resonant frequency is given. Okay, digital resonant frequency is given pi by 2. So now for the given specification, the first step we'll do the pre-warping. So that is a omega c is equal to 2 by t tan omega by 2. So tan omega by 2. So here this t is given. This t is equal to this t. So omega c is equal to, this is a 1 by 2. T is equal to 1 by 2. So 4 tan, the resonant frequency given pi by 2. So you will get tan pi by 4. Tan 45 1. So omega c is equal to 4. Omega c is equal to 4. Then put s is equal to 2 by t z minus 1 by z plus 1. So t is equal to 1 by 2, so 4 z minus 1 by z plus 1. Now you determine next step h of z equal to, so substitute h of z. So h of s is given, h of s equal to s plus 0.1 divided by s plus 0.1 the whole square plus 16. So instead of s, you substitute 4 into z minus 1 by z plus 1 plus 0.1 divided by s plus 0.1, s 4 into z minus 1 divided by z plus 1, s plus 0.1 the whole square plus 16. So h of z 4 into z minus 1 plus 0.1 into z plus 1, so divided by z plus 1 whole divided by 16 into uh, z minus 1 the whole square divided by z plus 1 the whole square plus 0.01 plus 8 into a plus b the whole square. So 8 into z minus 1 by z plus 1 plus 16. Again step by step you come simplify and compute. So I'll give the answer, you just cross check. So 0.128 plus 0.006 z inverse plus 0.1222 that is z minus 2 divided by the numerator polynomial coefficient, denominator polynomial coefficients are okay 1 plus 0.0006 z minus 1 plus 0.975 z minus 2. You can simplify. H of z is equal to z minus 2, take it outside. So 0.128 z square plus 0.006 z minus 0.1222 divided by z minus 2 and write z square plus 0.975. So these two will be cancelled. So you can simplify z square. So z square is equal to 0.975. So z is equal to square root of this is minus, so minus 0.975. Again this can be written as z is equal to j square minus 1 j square and so we get z equal to j square minus 1 now. So this is z. Calculate and write z equal to j.9874. So the real term either you can determine the poles, otherwise with this you can realize the system in direct form too directly. So for this how many delay elements, n is equal to 2 delay elements are required. So the coefficients, polynomial coefficients of numerator and denominator, and you can realize the system in direct form too and find the number of poles order is equal to, so pi k you can determine the poles also. Okay, the minus 1 j square is equal to minus 1 of the poles. So where the poles are located you can determine. Okay, so with this I think one more problem and pose the problems, some of the problems from John Perkins. You can practice. Again one more problem, John Perkins. You can refer the problem. Design a single pole low pass filter with a minus 3 dB bandwidth and a 3 dB bandwidth of 0.2 pi using bilinear transformation. So single pole means you know that what is the transfer function for single pole? omega c by s plus omega c. So omega c is the 3 dB minus 3 dB bandwidth. And 3 dB bandwidth of the unlock filter. So it's a first order filter. First order filter. So order means first term is n is equal to 1. So number of poles is equal to number of the order of the system. Single pole. So it's a single pole. So first order system. Single pole means h of s can be written as 1 by a0 plus a1s. And we include the normalized transfer function h of s equal to 1 by s plus 1. So because a0 is always 1. Okay, single pole system, the normalized transfer function equal to 1 by s plus 1, where frequency denormalization low pass filter put s is equal to 2 by put s is equal to s by omega c. So s is equal to s by omega c, we will get h of s that is equal to omega c by s plus omega c. So for 3 dB bandwidth is given. So for that omega c equal to, so 3 dB bandwidth omega c is equal to 3 rp 2 by t tan omega by 2 is equal to 2. So what is the t is given? So t is, if it is not given, you take t is 1. Okay, so 2 tan the omega is given. So 0.2 3 dB bandwidth of 0.2 pi is given. So 0.2 pi by 2, so which is equal to omega c is equal to 0.65 2 by t point. This is 0.2 by t, so 0.6 by t. 0.65 omega c is equal to 0.65. So h of s, now transfer function h of s is equal to omega c 0.65 by s plus s is 2 by t z minus 1 by z plus 1 s plus omega c 0.65. Okay, now simplify 0.65 to z plus 1 divided by 2 into z minus 1, 2 into z minus 1 plus 0.65 into z plus 1, z plus 1. After simplification, so 0.65, you can take z outside, 1 plus z inverse by, so this simplification will be 2z minus 2 plus 0.65z plus 0.65. Then write 0.65z into 1 plus z inverse divided by here 2.65z minus 1.35. The final point 2.65z, then take 1 okay, wait, another one more step, we'll write it here. 2.65 z, 2.65 z here, 2.65 z So you can take it common to 1 minus 0.509 z inverse. So this will be cancelled. So now you can get point. This will be 0.245 into 1 plus z inverse divided by 1 minus 0.509 z inverse. This is what catch off is it. Okay. So the design frequency response you can determine. So I think with this we can conclude the session. Take more problems from the book exercise and practice the problems. Thank you.